This view of a crescent Mars was captured on May 15, 2026, by NASA's Psyche mission as it approached the planet for a gravity assist. Captured by the spacecraft's multispectral imager instrument, this was the last view of the whole planet before it began to overfill the field of view of the camera. Because Psyche approached Mars from a high phase angle, the planet appeared as a thin crescent in the days running up to the close approach, lit by sunlight reflecting off its surface. In observations from the spacecraft's multispectral imagers, the crescent appeared brighter and extended farther around the planet's disk than anticipated because of the strong scattering of sunlight through the planet's dusty atmosphere. This close-up view of a dust storm on Mars was acquired by the Mars Color Imager instrument on NASA's Mars Reconnaissance Orbiter. The image is centered on Utopia Planitia, along the north seasonal polar cap edge in late northern winter. Similar small storms also form near the south seasonal polar cap edge. The dust storm pictured here was short-lived, lasting less than 24 hours. The image also shows the seasonal north polar cap at top of figure and gravity wave water ice clouds coming off of my crater just south of the storm. Gravity wave clouds, also called Lee wave clouds, are clouds that result from changes in atmospheric pressure, temperature, and height because of vertical displacement, such as when wind blows over a mountain or crater wall. NASA's Mars Reconnaissance Orbiter has revealed that movement in sand dune fields on Mars occurs on a surprisingly large scale, about the same as in dune fields on Earth. This is unexpected because Mars has a much thinner atmosphere than Earth, only about 1% as dense, and its high-speed winds are less frequent and weaker than Earth's. For years, researchers debated whether or not sand dunes observed on Mars were mostly fossil features related to past climate, rather than currently active. However, researchers using images from Mars Reconnaissance Orbiter's HiRISE camera have detected and reported sand movement. Using images from the HiRISE camera, scientists have now determined that entire dunes as thick as 200 feet are moving as integrated units across the Martian landscape. The study was done at the Nili Patara sand dune field, located near the Martian equator, where the team was able to measure the Lee front, which is the leading edge of the dune. To detect these subtle changes on the Martian terrain over time, scientists analyzed images of the Martian surface, shot by the HiRISE camera with a new analytical software tool that allows researchers to measure changes in the position of sand ripples in combination with a digital terrain model, or DTM. A HiRISE digital terrain model is a topographical map of the Martian surface at a resolution of 1 meter per pixel and tens of centimeters for the vertical resolution. In other words, a DTM makes it possible to translate the two-dimensional views taken by HiRISE from its orbit into representations that reveal features like hills, valleys, gullies, craters, or dunes for that matter, with an accuracy that would make a decent anthill show up as a feature on the surface. After scientists make the digital terrain model, they apply their software to correct for distortion. Combining those tools allows them to exactly measure what they see on the surface, which is critical for the detection of changes. The analysis with the new software tool has revealed that sand ripples move faster the higher up they are on a dune. The reason Nili Patara dune field was chosen for study was because the sand motion happening there could be quantified. Dunes there are also similar to dunes in places like Antarctica and to other locations on Mars. The dry valleys of Antarctica are a great place to study geological processes that may apply to Mars because they are very cold and very dry. The study adds important information about the pace at which blowing sand could be actively eroding rocks on Mars. Using the new information about the volume of sand that is moving, scientists estimate rocks in Nili Patara would be worn away at about the same pace as rocks near sand dunes in Antarctica, where similar sand fluxes occur. Scientists calculate that if someone stood in the Nili Patara dunes and measured out a 1-yard width, they would see more than 2 cubic yards of sand pass by in an Earth year, about as much as in a children's sandbox. Scientists could use this new information to understand broader mysteries on Mars, like why so much of the surface appears heavily eroded, how that occurred, and whether it is a current process or it happened in the past. Now, sand flux joins the arsenal of mechanisms capable of creating considerable erosion seen today on Mars. This pyramidal rock is located inside Gale Crater on Mars. Analytical studies performed on the rock by the Curiosity rover suggest the rock is an igneous rock but found to be high in elements consistent with feldspar, such as sodium, aluminum, and potassium, and lower concentrations of iron, magnesium, and nickel than other such rocks previously found on Mars. The mineral content and elemental abundance indicates the rock may be a mugarite, a sodium-rich oligoclase-bearing basaltic trachyandesite. Igneous rocks similar to the rock are well known but occur rarely on Earth. On Earth, such rocks form when magma, usually found in volcanoes, rises to the surface, cools and partially solidifies with certain chemical elements, while the warmer liquid magma portion becomes enriched with the left-behind elements. The rock is a ventifact with a volcanic fabric. Its pyramidal shape was formed by Aeolian drifted grains of sand. The little cavities on its surface were formed by the blast effect, which is caused by different flow dynamics at the microrelief. On the surface, one could see the marks of the main wind direction by which the rock was formed. NASA scientists have also reported that the rock may be a mugarite very similar to terrestrial mugarite rocks.